So around the nucleus, more than one nucleus, you've got nuclei. You have electrons. And electrons are an atomic particle that's not found in the nucleus, but is found around the nucleus, and they have a negative charge. So they have the opposite charge of a proton. And their mass, they're very, very light compared to a proton or a neutron. They're about 1/2000th of the mass of a proton or a neutron. So their mass is effectively negligible. It doesn't factor into atomic mass. But the charge, that is another story. When the number of protons and electrons is equal, they don't have any net charge. They are neutral. If you've got more protons than electrons, you've got a net positive charge. If you have more electrons than protons, you have a net negative charge. So to calculate the net charge, you calculate that by subtracting the number of electrons from the number of protons. And how do you do that? More on that to come. So this picture just kind of represents how we tend to think of an atom with its subatomic particles. So we've got in the nucleus, all huddled together, our protons, those red, pinkish red circles with the pluses on them, and neutrons, which are those brownish looking things with no charge, and surrounding them are the electrons. And the electrons are in constant motion. In the picture on the right, you can see they're represented as being two smaller, not to scale smaller, but smaller particles with a negative charge. But electrons are pretty much always just whizzing around at colossal, phenomenal speeds around the nucleus. And it kind of makes a cloud. So the picture on the left is showing you how the electrons, if you try to take a photograph of an atom, you wouldn't be able to see the electrons because they're just whizzing around too quickly, no matter how fast your camera was. So like I said, electrons, they orbit around the nucleus, kind of like planets orbit around a star, like the Earth orbits around the sun. But they go in lots crazier shapes than just in a flattened circle, right? So when our planet goes around the sun, it's just kind of in a flat plane, like a circle. It's not making a sphere. But electrons, when they orbit around their nuclei, they can go in spheres, they can go in lots of different crazy directions, which fortunately we don't need to know about or care about all that much. But the path that an electron follows is called an orbital, because it's orbiting. In the first orbital, the orbital that's closest to the nucleus, we find 2 electrons. And then when we get to the second and the third and the fourth and up to a few more, there's not a whole lot more, but there's more than just 3 or 4. We can get up to 8 electrons in those orbitals. Now, atoms are not most stable when there's no charge. So the positive and negative charges is not what makes an atom stable. What makes an atom stable is when the valence shell, which is another name for that outermost orbital, is full of electrons. And that's what we call the octet rule. We want atoms to be stable. We want them to be happy, so to speak. And they are happiest, I'm putting happy in air quotes because atoms, as far as we know, don't have feelings, but they are happiest when they have that outermost orbital full of electrons. And so bonding is what happens between atoms in order to make sure that that is the case. Okay, so a little bit more about all of these numbers, as I promised. You can see all of these have a number of things in common. They have those symbols with 1 or 2 letters, a capital and a lowercase. All elements have a name: gold, boron, uranium, radon. And then you can see there's a couple of numbers. So this number up here in the upper left corner, that is the atomic number. The atomic number is a reflection of the number of protons. What defines an atom as being an atom of a particular element? It all boils down to the number of protons found in the nucleus. So for boron, they have 5 protons in the nucleus. Uranium has 92. Radon has 86. Gold has 79. So number of protons is the atomic number, which is what defines an element as being element X. Boron, radon, iron, oxygen, whatever. Then there's this other number down here. And you can see those numbers are not nice round numbers. They've got a decimal place and 4 numbers after them. So what's going on there? So that is the atomic mass. And the atomic mass, another pattern you'll see here, is that the atomic mass is always bigger than the atomic number, besides being not a whole number, not an integer. So, for example, with gold, it's 196.9665. And the reason that those numbers are bigger is because, well, you can't be smaller because protons weigh what they weigh, which is 1 atomic mass unit, 1 Dalton. And neutrons weigh what they weigh. So how do we get these parts of numbers? Why are they not just whole, even numbers? Well, you may have heard that the average family has 2.4 children. Okay. And if you have an average family, you probably don't have this situation going on where you've got maybe mom, dad, sis and brother, and then 0.4 other brother. That's not what happens. What happens is when we say that an average family has 2.4 children, means that most families have 2 children. Some families, a lot of families have 3 children. And if we look over the cross section, if we take an average, the average number is 2.4 children. There are no partial children that go into that calculation. So we look here, we see all these different families. Some of them have just the 2 children. Some of them have other children as well. So the same thing is true for atoms. Okay? So boron is element number 5 because it has 5 protons in the nucleus. Okay, and as you can see, it's got some neutrons too. But not all of those atoms are the same. If you go back and take a look, you'll see that almost all of those pictures are identical, except I snuck in a picture where you've got not 1, 2, 3, 4, 5, 6 neutrons, but how many are in this one? 1, 2, 3, 4, 5, 6, 7. Oh, sneaky me. I snuck in another neutron. And it's still boron. It's still boron because the definition of boron is it's an element where the atoms have 5 protons. So it's still boron, but it's a little bit different. And we call these slightly different forms of atoms or elements isotopes. Iso means the same. Tope, I don't know what tope means, but isotopes are the same element, but they have a different number of neutrons, which means they have a slightly different weight to them. So I went from boron to carbon. Carbon is element number 6 because it has 6 protons in the nucleus. The most abundant form of carbon is carbon-12, which is here on the left. So carbon-12 has 6 protons, as all carbon atoms do, and 6 neutrons, which means protons plus neutrons equals 12. So that's the mass of the that carbon atom. This one here, if you want to count, it's got 7 neutrons. So 6 protons, which is by definition what carbon is, plus 7 neutrons means the mass is 13. This is carbon-13. We can add another neutron, and as long as we still have 6 protons, it's still carbon. And this is carbon-14. And down here, I've just shown you how we might express, a chemist might express these different forms of the same element. Carbon-6, carbon-12, carbon-13, carbon-14. They probably wouldn't put the 6 down there because 6 is just the definition of carbon. So it goes without saying that there's 6 protons there. So these different forms of the same element are called isotopes. And again, the electrons are so light that they don't really factor into the mass. There may be 6 electrons in each of these. Remember, that's 6 2,000th of a Dalton, which is really a very small number. So it doesn't really factor into the atomic mass. Okay, so another way to say that is that isotopes are the same element with a different number of neutrons, and therefore they have a different mass. Usually, for a particular atom or element, there are a couple of stable isotopes that that can tolerate having those extra neutrons, or the normal number of neutrons, and they'll just kind of sit like that. But like I showed you with carbon, some of those isotopes are unstable, and they will go through decay. And decay means they're going to lose particles. Typically, it means they're going to lose a neutron. And when they do, they release energy. They do stuff. And that decay is what causes radioactivity. So you've probably heard of radioactivity. What is radioactivity? Radioactivity is something that occurs naturally. We can measure radioactivity with a Geiger counter. You've probably seen a Geiger counter on TV or in the movies, and it goes clickety click, click, click. And when it clicks really fast, that means something is very highly radioactive. If it's just a few clicks, it means it's not very strongly radioactive. But radioactivity occurs naturally. There's radioactivity around us, all around us right now, at low levels. And at low levels, radioactivity is not a big deal, NBD. And we can actually use radioactive materials as tracers. So imagine that you're trying to find your friend in a big crowd. So you're going to the football game, and you want to find your friend. And you ask your friend, what are you gonna be wearing so I can find you easily? And your friend's like, I'm gonna be wearing orange and blue. And you are probably laughing and saying, that's not help. And then your friend says, no, I'm gonna be wearing a big green foam cowboy hat. And that's gonna make it a lot easier to find your friend at Jordan-Hare Stadium, right? Is a big green foam cowboy hat. So radioactive atoms are kind of like big green foam cowboy hats in that they're a lot easier to identify out of a crowd of atoms than just the normal sort of blue and orange atoms that are around. So we can use those radioactive elements as tracers. We can also use different isotopes to date very ancient items because the rate of decay is very, very consistent. It's more accurate than just about any clock. In fact, the clock that your cell phone runs on is based off of a universal atomic clock. Okay, so the clocks that you might wonder, how do all the clocks in the world know to change at exactly the same time? Have you ever done this where you look at your phone with your friend and you see if they change numbers at the same time when it goes from 10:01 to 10:02? Because they do. And we do that because the motion of atoms is very, very precise and measurable. And we can use that very, very regular decay to date ancient items, fossils of things, dinosaur fossils, fossils of mammoths and mastodons, and much older, much much, much older. We can date the whole universe based on the decay rates of different isotopes. So that's pretty cool. In high levels of radiation, that's not so good. Examples are the Fukushima power plant in Japan. In my generation, we had the Chernobyl power plant in Russia. Chernobyl is still very strongly radioactive. People can't live near that power plant. They have to live outside of what's called an exclusion zone. Same with Fukushima, because the radiation levels are so high that you could not survive. The radiation would, the release of energy and particles into the air would damage your DNA, and that would likely, it would be lethal to you. Nuclear weapons also function on this principle of radioactivity and radioactive decay. When you split an atom, it's going to release an awful lot of energy. So high levels of radioactivity are bad news. But also, this is what's powering our sun right now, is radioactive swapping of subatomic particles at the core of our sun.